Samples. Sample 1. Find the capacitance per unit length of two identical parallel straight wires of radius A and the separation D. D is much larger than A. What we do, as we suggest, first we assume the Q on pole. One positive Q, one minus Q, and then we try to find the E between them. Okay. Once we get the E from Gauss law or something, and we find the V. We know Q, we know V, Q over V is C, right? Now, suppose this is a positive charge here, this negative charge here, okay? The E equal to lambda over 2 pi epsilon R. Now, this is positive, okay? Lambda is the charge density per unit length, okay? And this is R distance. So you have this, at this point, we connect this line. At this point, E produced by the positive charge is this one, lambda over 2 epsilon line. And E produced by this negative charge equal to minus lambda 2 pi. This distance, this is R, this is D minus R, okay? And so the total E, because this E is outward, and this E is inward. So the absolute number they put together is a sum. So the absolute E is this number plus this number. This is the E. Now from E, we want to find the V, the potential difference between them. Along this line, we know that V, okay, this is the E, okay. V equal to integration E dot dr. In our case, E is along the direction R. So E dot dr equal to dr. And the integration is from here, A to D minus A. Okay, D minus A. So positive to negative. A to D minus A. Okay, and we put the E, we just calculate inside. E equal to lambda over 2 pi epsilon A, 1 over R plus 1 over D minus R, okay? Then we find the V. This is a tedious, okay, simple calculation. So we find the V between these two. Once we find the V, we know Q. Q over V is C, okay? Q over C. This is the Q, is lambda times 1. This is a requirement per unit length, okay? We put this one, okay? Inside, we cancel the lambda, we get this one. This is the C. This is the answer, okay? Sample. The plates of a parallel capacitor, this is a parallel capacitor, carry Q and minus Q respectively, and the same area S. So this is area S, okay. The separation between them is D. This is a D, okay? Yeah. A uniform dielectric of constant kappa, thickness K of area half S is inserted parallel to the gap as shown in the figure. Find A, the potential difference between the two plates. B, the capacitance. C, the induced charge density sigma prime on the surface, okay, of the dielectric. Okay, now what we do? Now, one thing you have to, this is a plate, so it's equal potential. This is equal potential. The charge density will be different. Why? Because the situation is different. So we're divided into half is sigma 1, half is sigma 2. Okay, we don't know what's happening, all right? In case they are equal, possible, but in general they were not equal, all right? Yeah. Now we go back. The electric field E0 in the gap between the plates and the dielectric slab I want to find. as we calculated before. This is a Gauss law, epsilon 0, kappa E, say, in this space, k equal to 1. Okay, so we found the E. And this Q is the charge in this line. All right? And then we find epsilon 0 equal to Q over epsilon A. Q over A is the charge density, sigma. Okay? Now, the electric field E1 in the dielectric slab should be epsilon 0 kappa E1 over dA. We calculate the same reason equal to minus epsilon 0 kappa E1A. Okay, this is equal to minus Q. Why? Because this is only free charge. Okay, this is not free charge, minus Q. And then we found E1 inside is equal to Q over epsilon 0 Ka equal to E0 over kappa. This is what we learned in the class. Now we go back to this one. This is called part 1, part 2. Part 2. They're different. Okay? So we take, let's see, sigma 2 times area half A plus sigma 1 times area equal to total charge. Right? And we look at the potential. Those potential different from right side and from left side should be the same because they are equal potential, right? And now let us find from left side and from the right side, see the V should be equal. Before we do that, let's review the E. E1 here equal to Q over epsilon 0 A is a formula. And we find Q over A is sigma 1. So E1 is sigma 1 over C. All right, same thing. Here, E2 inside this one should be sigma 2 over epsilon 0, and so on, kappa. Okay. Now, so this one is E2 here, E2 here in the vacuum. That length is D minus T. This is plus sigma 2 over kappa epsilon 0. This is E inside times T equal to the V. This is on the left side. And on the right side, it's simple. This is equal to epsilon of E1 times T. Times T. And then we take V out. They are equal. So finally, we get two equations. Sigma 2 plus sigma 1 equal to 2Q over A. Sigma 2 of D minus 2 plus sigma 2 over K. Kappa T equal to sigma 1D. These two unknown two equations, we can find sigma. Okay, sigma 1. Okay, this is a tedious algebraic work. I'm not going to do it. It's a simple one, but a tricky. Once you know sigma 1, then we find the V. Why? Because we have the E, we get the D. E, what I see, E is sigma 1 over epsilon 0. This is the one. This is E. We have E, sigma 1, put inside. We got a V. All right? We got a V, we got a Q, we got a C. C equal to Q over V. Put the V inside, cancel out the Q, we get a C. I'm not going to get into the detail because these are all algebraic, okay? Sample. A cylindrical capacitor is composed of a conducting cable of radius A and coaxial cylindrical layer of radius B, B larger A. Now, this is radius A. This is radius B, okay? This is as a layer is a cylinder, okay? This is a cylindrical capacitor. The length of the capacitor is L, okay? There are two cylindrical layers of uniform dielectric of constant kappa 1 and kappa 2 respectively. Now, you have two cylinder with different kappa, filling the space between the conducting plates with a separation radius R0. Now, this R0. Smaller R0 that A is 1. Larger than R0 and smaller than B is 2. Okay? Yeah. That dielectric constant kappa 1, kappa 2 respectively. Filling the space between the conducting plate with separation radius R0. Find the capacitor C. Well, we do the same rate. First, we assume the Q in positive, negative. And then we find the E. And then from E, we find the V. One have a V, we have a Q, we get a C. Now let's review a cylindrical capacitor. What we do, okay, we just suppose its length is L. Yeah. It's formed by two coaxial cylinders of radius A and B, the Q. Okay. We assume that the L is much larger than B, larger than A, so that we can neglect the fringing of the electric field that occurs at the end of the cylinder. Each plate contains a charge of magnitude Q. Inside is positive, outside is negative. Now, in order to find the C, as usual, we suppose the charge positive Q, negative Q. And we find the E. Suppose I want to find this point, the E. Okay? Because the symmetry, we make a Gauss surface as a cylinder, right? With the same R. Okay. And the flux, so this Gaussian surface is, we have 3 parts. 2 parts are 0. Okay? Yeah, 3 top parts, because E perpendicular to dA. Side part is okay. Bottom part, E perpendicular to dA, because dA is outward perpendicular surface. A is on the surface, or E is the surface, so they're perpendicular. So we get equal to E dot dA. And E is along the radius, okay? dA in this part along the radius. So E dot dA equal to E dA. E, by symmetry reason, all E are the same in magnitude. So E take out, integration dA is A, so we get a dA. A is the area of side surface, which is 2 pi r L. So this is, once you have a 5, yes, then if it is in dielectric, so you put the kappa, replace epsilon 0 by kappa epsilon 0. We get this equation, and we get E. Okay? Now, from this then we go back out question. E1 and E2. E1, you put a kappa 1. E2, we put a kappa 2. That's electric field in these 2 different layers. And then we will find the V. Once we know the E, we want to find the V. V equal to E dot dI integration from positive to negative. Whatever layer, E is along the radius, so E dot dr equal to E dr. We take the road along the radius, so E is along the radius. E dot dr equal to E dr. The integration is from positive to negative. Okay. In our case, the positive to negative, we have 2 layers. Okay. This one is from A to B. In A to B fit 2 parts. It's E is A to R0. Okay. And E2 is R0 to B. Okay. We put E1, we put E2. It's very easy to integrate. It's a log. Okay. Then we do the calculation. We put E1, E2. Okay, this is E1. Okay. A to R0. And E2 is R0 to B. This is a dr of R log R, dr. So we get this V very quickly. 2 terms. And you see, they have a lot of common. Q, 2 pi L, epsilon 0. We'll take this out. Q, L, 2 pi epsilon 0, and inside this one. This is the V. Okay? We know V, we know Q, we know C. Okay? C is Q over C. Cancel off. This one put back. Okay? It's just 2 pi L, epsilon 0. And then we match this one. We get the answer.